Hello, everybody. My name is Iliyan. I am working as a software engineer for a LA-based company called Liferay. And today, I will talk about HTTP 2.0 and QUIC protocols of the very new feature, which will replace the protocol which is currently used by World Wide Web, HTTP 1.1. So first is that question. Why do we need a new version of HTTP protocol? What is wrong with the protocol? After all, it's used by World Wide Web since 1990, right? It works pretty well. It's very simple. Actually, browser sends a request to the server, and server responds. This is it. Very simple. But if you check this chart, which is just for 4 years, you will see that there is not only one request and one response. There are actually multiple requests and response, about 80, 90 for the top 100 sites, according to HTTP archive. So this comes to tell us that the web has changed drastically. It's a web platform. It's not more platform for reading different cross-linked documents. And because of that, we have to admit that HTTP 1.1 has issues. Those issues are so big that, unfortunately, we need a new version of the protocol. And those issues are so many that I will mention only 3 of them. The first one is that it's very latency sensitive, right? Imagine that we have a server in LA, and our client is right here in Berlin. All those requests should go from Berlin to LA, then get back. This is very expensive, and latency and protocol is very latency sensitive, right? Apart from that, the specification is huge. The original specification has been replaced by about 10 different RFCs for message syntax and logic, for semantics and content, and so on. There are optional parts, like HTTP pipelining, which are sometimes implemented, sometimes they are not. And more like buggy proxy servers. So this is the key. Latency kills, and bandwidth is not everything. If you check this chart from, I guess most of you are very well aware of it already, from some point, how fast is your internet at home for daily browsing doesn't matter. If you have about 5 megabits, it's pretty much enough. I'm not talking about streaming, of watching, or downloading huge video file for daily browsing. What matters is the round-trip time. It's for every 20 milliseconds, as you see, the page loading time increases. So we are stuck by latency. So what could be solution? It's obvious that sending one request and more in returning response is not enough. So what could be the solution? One possible solution could be HTTP pipelining, right? Since that's exactly its purpose. Instead to send one request to the server and waiting for the response, browser sends 3 or more requests and waiting for 3 or more response. Sounds very good in theory, but unfortunately, it's not like this. That's not the solution. So why not? It's not because by the specification, the server must send its responses in the same order that requests were received. So this is it. In fact, the entire connection remains first in, first out, and head-of-line blocking can occur. What exactly this means? Imagine that we have 3 requests, and the first of them requires some heavy database request on the server, right? The rest of those could be just one JavaScript and one CSS file. They will be blocked. There are more buggy proxy servers which partially implement or not properly implement HTTP pipelining. And as a result, in most browsers, HTTP pipelining is disabled or not implemented at all. So keeping that in mind, what could the browsers do? What can they do in order to improve the performance? There is no way except to achieve multiplexing by open multiple connections to the servers, and that's exactly what they do. So this is the one side of the question. The second side, or the next side, is that developers, as very creative people, they implemented a lot of workarounds, so-called optimizations. Most of you will be very well aware of them. They are creating images, sprites, sharding, resource inlining, concatenating files, combo services, preloading resources when the user is idle, reducing cookie size, or even using cookie-free domains exactly for that purpose, using linked state import to pack components into multi-part document, and so on. In fact, a whole industry has been created to deal with those issues. Sites have been created, performance groups in the big companies like Google or Yahoo have been created. But if you're a regular web developer and you want to make your sites faster, as soon as you read all those guidelines, you start looking like this. Why should I do all that? Why is that needed? And if you also got tired of all that, then say welcome to HTTP 2.0 and QUIC protocols. HTTP 2.0, which will replace 1.1, is currently on draft 14. It's being actively developed. It's not yet finalized. Probably it will be this year, maybe the next one. And its purpose, or its objective, is very simple: to fix the issues in version 1.1, but without breaking the web. Sounds very ambitious, and this protocol is actually based on Speedy, which has been developed by Google in 2009. The very first draft of HTTP 2.0, version 0, was based on the latest specification of Speedy. So, going inside to the protocol, how browser switches to that new protocol? There are two ways, from HTTP and HTTPS. If we switch from HTTP, we use the very well-known HTTP upgrade mechanism. However, this means a round trip. So that's why it's better to look for another solution. And if we switch from HTTPS to HTTP 2.0, an application layer protocol negotiation extension is being used, which avoids this drawback. The protocol has many exciting features, and those, I will note some of them. The main difference with version 1.1 is that it's binary protocol. It's not text one. So for browsers, it makes huge difference. For us, it makes that if you use telnet to log to some server, to log into some server, that won't be possible anymore. But because it's binary protocol, it's much easier a parser to be created. If you're a Node.js developer and you want to create your own server, it will be much easier for you to create a binary parser based on this binary protocol. There won't be needed to deal with string delimiters, with strings at all. On the very low level, browser and server exchange frames. And each frame belongs to a stream. If there is a frame which doesn't belong to stream, that's protocol error. What is really important is those streams are multiplexed, right? We have one single connection, but multiple streams. They are multiplexed, and they also have priorities. This is really important. As you know, every page, there are some resources which are critical for rendering the page, and there are others which are not. CSS are critical. JavaScript could be critical if the page requires JavaScript, but the images usually are not. So now we can balance with those different streams. Something which we were doing for years, it was called resource inlining. Now it's on the protocol level, and it's called server push. Again, if I have a Node.js server, I can check if the browser allows server push and to push my critical resources when the page is being loaded, right? Instead to put everything on the page and to deal with caches and something like this. This is what we have to emphasize. One connection to the server, that should be enough, and not 6 connections per domain as most browsers do now. Some of them actually open more than 6 connections. But in general, this is not good for no one, neither for the browser nor for the server. The browser has to deal with memory, to balance those connections. That's not good. Now, just one connection. We go back to the point as it should be. As I said, frames that's on the very low level, and this is how a frame looks like. We won't take a look on all of this one by one. I will mention just 2 of those: the type of the frame and stream identifier. Every page has a stream identifier, so as I said, this would be protocol error. There are about 10 different frame types currently in the latest draft, like data frame, which conveys arbitrary data associated with a stream. There are frames which deals with headers. Some of those are related to stream priority. Some of them are related to promises, to push promises. This is related to server push. Some of them their purpose is to reset a stream, just abort the stream. I don't want to see it anymore. And those frames are grouped in streams. So streams, by definition, is logical bidirectional sequence of frames, which are being exchanged between the browser and the server. So one single connection can have multiple open streams. Like in this example, you may see that we currently have 3 streams: stream 1, stream 2, and stream 4. So they all contain some frames, and they are multiplexed. One stream may represent an HTML page. Another stream may represent a JavaScript file, or a third one, some style. But they are multiplexed, and they are being prioritized by the browser. So going to priorities. Each stream has priority. That priority is specified by the browser. And what is important is that priority can be changed runtime. So the exact order in which frames are delivered can be further optimized. The priority is an optional 31-bit value, and stream with priority 0 has the highest priority, right? Streams also have dependencies, and like in this example, we have 2 streams, B and C, which depend on A. So if we have another stream called D, and it just has priority, it will have the same value as B and C. However, if we say that D depends on A, then B and C will start depending on D too. Another key part of the protocol is related to the headers. As I said, we cannot break the web, right? This is the deal. So HTTP 2.0 is stateless protocol 2. Nothing has changed here. The client still has to send data to the server. However, there is a big difference. The headers in version 2.0 are now compressed. This is the big difference. Just a few words about the compression. It's stateful, it's not stateless, which means that a single compression context for the entire connection is used, and the algorithm is specially designed for the protocol. It's called HPAC, header compression for HTTP 2, because of some evil guys who applied attacks like crime and breach. So we have a specially designed compression algorithm for the protocol. Going back to what we know very well, server push, we did that for years. Nothing new here. I guess all of you applied some, or embedded some resources to the page CSS or JavaScript or SVG image or whatever. So here, this is the difference. Server preemptively sends resources to a client in association with a previous client-initiated request. So if I'm requesting index HTML on the server side, me as JavaScript developer who works on his Node.js server, I can push the critical resources which are needed for the page to be rendered. Right? There is a trick here. The client explicitly must allow it. So on the server side, when we implement our servers, we have to check if that is allowed. Otherwise, that could be reset stream or something else. A client cannot push. A client, which means the browser, it cannot push resources to the server. Only the server is allowed to do that. So, very briefly, this is it. HTTP 2 rules, right? Because now, as developers, we have full power to apply different kind of optimizations, different than those which we were currently doing, or we can apply more, we can get some heuristic from how the user behaves with our page to push resources, to optimize our pages in different way. This is not the end, because now we have, because the research continues, we have another protocol also started by Google, researched by Google. It's called QUIC. QUIC is a natural extensions of SPDY and HTTP 2.0 research. This is also multiplexing transport protocol, but there is a big difference. This protocol runs on top of UDP. It doesn't run on top of TCP as SPDY and HTTP 2.0 does. They don't. This protocol runs on top of UDP. Because it runs off UDP, the browsers cannot use those out-of-the-box features which are available in TCP, right? So those should be implemented on application level. So why should we do that? Because it's very hard to update TCP. It's everywhere. It's on servers, routers. It needs years until it's being updated. But now we can apply the results of the research, how to improve the web on QUIC. Google applied to their servers, applied to Chrome, and now everything is clear. If you can use, you can see how QUIC works right now in your browser. There is a flag. You can enable it if you want. I actually do it to see how is it going. So that's not the first time when people are trying to fix the issues on using UDP. People haven't slept those years, and there were already existing solutions like HTTP over DTLS. That's one possible solution. Those are two different protocols. After all, HTTP provides, among other things, stream multiplexing, right? DTLS provides SSL quality encryption and authentication over UDP stream. So why not use those protocols? The answer is very simple, because roughly 4 round trips are needed to establish an HTTP over DTLS connection. You can imagine how expensive, again with the example of Berlin client and LA server, that's too expensive. In contrast, the goal of QUIC is to perform a connection establishment with 0 round-trip time overhead. This is the goal. QUIC has all the benefits of SPDY and HTTP 2.0, but there is a big difference. There is no head of line blocking in QUIC. As you can imagine, delaying of only one packet causes the entire set of SPDY streams to pause, SPDY HTTP 2 streams to pause, because TCP only provides a single serialized stream interface. But in QUIC, when a single packet is lost, only one stream is being delayed. We can illustrate that with an image, and here is how does it look like. Here we have 3 streams with red, green, and blue color, and if a packet in the stream marked with red color is being lost, the rest 2 streams are not being affected. Here we can compare how QUIC behaves versus TCP plus TLS. For repeat connection, it's 0 milliseconds round trip time, right? For TCP plus TLS, it's 200 milliseconds. For new connection, QUIC is 100 milliseconds. For TCP plus TLS, it's 300 milliseconds. That's too much. As I said, because this protocol runs on top of UDP, many of the out-of-the-box features in TCP are now not available, so they have to be implemented on the application level. So QUIC also provides encryption, which is comparable to TLS, but with more efficient handshake. It has replay attack and IP spoofing protection, and it also has something very important. In order to minimize all those round trips, which really decrease the performance, there is forward error correction, which means the price of additional packet, for example, we can restore a packet which has been lost. So the server won't have to send this packet again. A really cool feature for us, like especially for us who use mobile phones, if that the communication channels are not defined by IP plus port, but by an ID. So in this room, there is Wi-Fi, and if you leave the Wi-Fi zone and go outside of this building for using mobile internet, that won't be so bad because the connection continues. So all this sounds very cool, very exciting, and I wanted to see what is the current status of those 2 protocols, where we're going, how are we going, and especially for this presentation, I created a small site which has the really cool name http2rules.com. So it consists from 2 pages. On the first page, we have it represents actually an online shop with a few CSS, JavaScript, and images. And the second page, I have a few web components. They are supposed to be the future of web development. So I wanted to see if we serve the content via different protocols, it will make some difference. So from my point of view, that site is like open source platform for testing different optimization strategies for HTTP 2.0. This is the idea, same content, but served via different endpoints, via HTTP, HTTPS, SPDY, and HTTP2. That's really cool, isn't it? I don't have QUIC endpoint yet because there is no production-ready server. Not that there is HTTP 2.0 production server. I implemented this on Node.js, so I had to build a version of Node with ALPN support, but it currently works. On each page, we can see the load time for each page, so we can compare. And because because we have great tools like webpagetest.org, now we can check what is the difference. How I intentionally did not apply any of those dark workarounds we were doing for years. I did not create any sprite for images. There are about 30 images. I did not create any sprite. I haven't concatenated any single file. I wanted to start with something simple and see how does it behave, right? If we avoid all of that. On top, we can implement further optimizations. So this is what web page test shows as waterfall. When we use TLS, HTTPS, this is the waterfall. You can see how does it look like. You can also see that the browser, Chrome, opened 6 connections to this domain. And now for each connection, we have initializing. We have SSL negotiation, which is expensive. TCP needs three round trips, right? So this is not so good. 6 connection, you can imagine how much time we are losing for all those connections. And here, I have a waterfall, again with web page test, which represents HTTP 2 waterfall without server push. On the server, I haven't pushed any of those resources. I just relied on the browser to do its best. Currently, this only works on Canary. It doesn't work on Chrome. I hope in a few months that will be available in Chrome too. But for now, we have to use Canary and apply a special flag. If you go to Chrome flags, you have to enable speedy/4, which is the internal name of HTTP2 for Canary. But now it works. It supports draft 14, which is the latest one, so that's really cool. Here, you can see that the browser created only 1 connection to the server, not 6. This is the big deal. So all those resources were multiplexed and returned to the browser via just 1 connection. This is huge improvement. But I wanted to see how does it behave if I push some resources. So here is the waterfall, what currently web page test shows. Probably that will change, because if you open Canary DevTools, you can see all those resources. But in web page test, it looks like that the browser made only 1 request to the server, which is index.html or /. But not. Actually, I intentionally pushed all CSS, JavaScript, and images file when the browser requests index.html page. So again, we have a connection view. It shows only 1 connection, not 6. If we have to draw the line, I would like to say the following. If you remember the workarounds which we did to speed up our sites for years, all those workarounds, ask yourself how HTTP 2.0 will affect the way you develop and optimize web applications for you or for your company. Thank you very much.